I consider myself really highly honored and privileged today's chief guest, Dr. BVR Mohan Reddy garu, to welcome philanthropist Padma Shri Dr. BVR Mohan Reddy garu to the occasion, please.
I'm really honored to be invited today by the Mechanical Engineering Association for being the chief guest at the 27th National Conference. Congratulations to organizers for doing the 37th National Conference. My apologies to Mr. Ram Reddy stopping him from introducing me. But let me say two sentences about myself, which I feel very proud about, which is very relevant to what we're talking about today. I also received an award from American Society of Mechanical Engineers. It's called the Leadership Award for my contribution in computers engineering. That's one thing which I feel very proud and relevant to this audience. And the second one is I serve on the board of University of Michigan College of Engineering as the Leadership Advisory Committee. That gives me enormous amount of satisfaction in terms of telling all people around me on what we can do with mechanical engineering. Having said that, I do have a little bit of pressure on time with me. There's somebody flying in from Mumbai, so I've got to keep up the time with them. I will talk to you in the next, say, 15 minutes or so on what I believe are the advances in battery technology and the future role of mechanical engineers and engineering. I believe that is something which has been talked about quite a bit. I'll express myself too on what I believe is future for mechanical engineering is. Who has a control on the slides? Yeah. My remarks today will be in the 6 areas of, I'll give you a global outlook of electric vehicles. What happened as a brief history of the electric vehicle so far? What are the goals that we set for ourselves? What do we see as the role of battery technologies? What do we see as trends in mechanical engineering? And finally, what is battery engineering trends? So if you look at the current status of the electric vehicles globally, enormous amount of progress being made. In the last 3 years, we literally tripled ourselves in terms of usage of electric vehicles. Currently in 2021, there are about 16.5 million electric vehicles. I may have a small contrarian view compared to engineer Ranga Reddy garu on the use of the hybrid electric vehicles. Our research believes that the hybrid electric vehicles will drop off as we progress into future. If you look at the history of hybrid vehicles, the reason why it was done was that takeoff, when actually you require traction, torque, electric vehicles could do it much better, and also that's the point of time when you see a lot of amount of emission that happens. At a cruise level, you don't require so much of torque, and you have fewer amount of emissions. That's how this hybrid came into play. There's a car called the Toyota Prius. And Toyota Prius did extremely well. Actually, at one point of time, I know there used to be an 18-month waiting time for people to get the car. But we've also seen that in case of hybrid, two things further happen. The maintenance costs are very high because you're now maintaining two systems, not just one. There's a ICE and there is a EV. And the second one is the benefits that come out of it are not in line with the investments we do. Typically what we have seen is the type of advantage it provided if probably an EV gave us about, say, a 15 kilometer for whatever measure that we use, it was up by about either 20% or 25%. So 20-25% was not something which we thought it to be beneficial. And that's how we're seeing a complete drop. So if you look at the other chart I have on the right-hand side of the presentation, it's the battery EVs which will take a steep upturn, whereas the plug-in hybrid EVs will start taking a downturn as we progress into 2030. And the other observation I have is the continuous growth of EVs would happen. We'll probably see if people keep up their commitments to COP21, then there's a possibility that the EVs will go all the way to about 65 million of them globally by 2030. That's a very, very heartwarming news for all of us. If you look at the bottom part of the chart where I have logos of several large auto company. Why did I have them there? Is primarily to tell you that a company like Volvo, which you see their logo in the center, has made a commitment that they will not be producing a single ICE car after 2030. It will all be EVs only. Or for that matter, I think all these other brands, whether it is Volkswagen or it's a BMW or it's a Ford or a Mercedes, all of them are not introducing new ICE versions at this point of time. So we have to definitely recognize that the future is more on the EVs itself, irrespective of which part of the world you live in. More interesting is that the amount of pressure and the amount of investments that are required to be done right now, people have started forming consortiums. And that's how specifically I called out Stellantis. On the right hand side, the bottom right corner you see Stellantis. That actually is a consortium of GM, Jeep, Fiat. All of them have joined together to make sure that they can produce a vehicle which will not be prohibitively expensive, because then they can write off their investments across many formations. All of these people are working together on their electrification, the software strategies, and also on the innovation of ecosystems. And also, we believe that this is a game-changing partnership. And this might surprise some of you. Very honestly, it surprised me when I read for the first time. Actually, the electric vehicles have a history which is much longer than the ICE vehicles. In the first industrial revolution, we saw electricity come in. Electricity came along with electric motors. And electric motors were used for driving vehicles around. So electric vehicles actually were very popular in the 19th century, the later part of the 19th century. Actually, people fitted electric motors on their horse-drawn carriages to supplement even power. I believe this story goes, somebody wrote, that it used to be extremely popular with ladies to drive these electric cars. Short duration, just go for a kitty party, or go and have an afternoon meal somewhere. That's what they used to do. It used to be extremely fashionable in New York. Short distance, but then the challenge was it could be long distance and so on and so forth. But the turn of the century, that's the beginning of 20th century, what happened was Henry Ford came out with this brilliant idea called assembly line manufacturing. It's called the T line that Ford called it. That was 1920, Ford's innovation. And that actually dramatically brought down the costs of the IC engine cars. To give you a flavor, in 1921, I do have an advertisement with me, which is a Ford car costed $625. But an equivalent electric vehicle was at $1,750. So literally an EV was 3 times the cost, and that is how the ICEs came into a lot of prominence around the world. And added to that, I can even say this in front of my good friends from Houston, the oil lobby of Houston made sure that they partnered with the auto lobby of Detroit, and between them they said, let's reduce the cost of oil itself. So oil prices came down, ICEs became very, very effective, cost effective, and the result is that the ICEs started taking off. But then the challenges from 2017 onwards, people started realizing the challenges that we have with the combustion engines. The challenge being that there is emission which is contributing to the global warming. And they said, let's move on back to ICEs to EVs. But by which time, I think culturally, we've all got corrupted to driving hundreds of miles at a stretch without any brake. The roads became much better. We wanted to have more conveniences in the car, whether it's to do with air conditioning or with the music systems. Every part and parcel of the car had to be automated. So which means it required power. And running a gas engine or gasoline engine for all this power made that there is going to be more amount of pollution. So they were raising concerns of pollution by 2017. Global warming came into well-being, and people started saying what's more important for the world is sustainability, social, and governance, ESG, environmental, social governance. But certainly the EVs, as they transition into ICEs, there are several challenges. The first one is the battery weights are very heavy still. I saw some please go back to the previous slide. I saw some new developments in the recent past, and I was very impressed. I was at an event Monday this week in Chennai, venture capital company, which funded a 2-wheeler EV motorbike which can get to 180 kilometer speed, it's the high-end one, 300 meters of reach that it had. But then the battery was no more than, they said, 5 kgs in all, and it was 18 inches by 12 inches by 4 inches, all fitted below the seat of the driver. And it had 500 fuel cells in it. So you can just imagine, actually I have a slide, I don't have time, but I do have a slide which what is the size of a typical lead acid battery versus what we are seeing today. It is truly, you can use a word called miniaturization. The second challenge is about the trips that it can undertake. The shorter trips became for the EVs, and then the third one was long duration charging time. And I'm sure there's some very serious breakthroughs that have happened in the recent past. And certainly the last one was the poor battery life. So this is how batteries have had history so far in the world. You started off, actually many people do not recognize that batteries were true in the 18th century itself. By 1784, we had the first battery that was created by Benjamin Franklin. And thereafter, truly the invention of the rechargeable lead acid battery came in by the middle of 19th century. The invention of nickel cadmium was in 1899, late part of the 19th century, but then it got commercialized only in 1990. That's how the nickel cadmium cells became so popular thereafter. So the battery has a fairly large amount of history. And if you also look at it a little bit more closely, it's all to do with metals. Whether it was to do with nickel, it was cadmium, it is lithium, it is iron. So therefore, when you think about batteries, I'm bringing in a new concept called metallurgy is very, very critical. And I'm sure having Professor B.S. Murthy, whom I respect as one of the best metallurgists I know of, speaking to you this afternoon. What do we see as we progress further on the batteries is not only the commercialization of life, which is lithium, iron, phosphorus battery, which came in 2005, but we will see a lot more advancements. And I think one of the areas that we are right now believing is it will become lithium air batteries. Move on, please. So batteries, as I talked about at length, so I'll probably say very briefly on this slide, have been largely to do with electrochemical processes. But you have also to remember that a fairly large mechanical and electronics work within a battery. Please do not imagine that very traditional battery that we all knew of in a car with lead acid is the battery that we have today. It's all come down to a miniaturization of about literally 10 millimeters by 15 millimeters by 3 millimeters in a cell, and all that has to be managed, all that has to be packed, and all this has to be controlled. And you have to have a proper way of charging every one of those cells. So there is mechanical stuff, because you have the packaging that goes by, the chemical technology, the metallurgy technology, and finally the electronics that are there. So batteries have become extremely complex. It's not very simple technology. The next one is, what are the goals that we have at this point of time for battery technology? The key thing is that we need to reduce the cost. Cost has become exorbitantly expensive. And lots of new ideas are coming in terms of basically what is it, the battery is all about storage. And I've heard different types of ideas from people, and it doesn't seem to stop there. We're right now converting the peak time solar energy in pumping water to reservoirs and converting them later in the night when you have peak load demand for energy into power, hydel power. So if you convert the solar power into a hydel power. A more exciting one that I heard in the last few weeks, an Australian friend of mine was telling, they have this unused coal mines which have shafts for bringing up the coal, which were as deep as 1,000 meters to 1,500 meters. And all of them, what were they doing? Bring up the coal. So instead of that, what they do now is when they have the excess energy coming from solar, they lift the weights during the daytime, and in the night they drop them. And when they drop them, that energy is converted into power, and power is usable by the peak load demand. So there is the challenge in terms of making sure that we have enough of storage. Storage is relating to the cost. I'm sure Elon Musk talks about actually storage. Every wall in the home has to be the storage. You don't require any more of connection. I think that's the future of these technologies. Certainly what we believe further is that the further challenge with this, especially when we talk about electric vehicles, is it has to become lighter in weight. Weight is still a big challenge for us. We've got a two-seater, I don't know what to call it. It's a vertical takeoff,
horizontal process that it goes by. It's a sort of a chopper, helicopter, without an IC engine, all right. It runs on 12 different motors, 8 of them for vertical takeoff, and then for horizontal propulsion, there are 6 more that happen. And all of them work on electric power. You can just imagine now how much of power has to be packed, and then thereafter, extrapolate yourself as to how much weight you can carry. You have to be light-weighted, but at the same time, you have more amount of power. We're certainly seeing that safety is another issue with the electrical batteries. There could be extremely unfortunate situations one could land up in. And I'm sure several of you have read about this. These batteries, which are especially neighboring countries' batteries, they come from China, we can call it out, and produce a lot of heat. And the heat could start creating fire. And somebody very wrongly, I would use a bit worse word than that, started charging these batteries in their home. And that caught fire to an air conditioner and people got killed. And in the process, that company is almost on the verge of shutting down. I know the company too. I think there are many challenges that are there in terms of battery technology. In addition to that, we also have the role of attaining net zero emissions. So you have a battery which requires first to go through maintenance, and after that it may have to go through repair, then it has to be refurbished and finally replaced. But finally what comes back as the landfill is no more than 20% of what you use as material. That's the current norm. So therefore, this is basically what we call it as the circular economy. We are now working with our customers all around the world, not necessarily just on batteries, but many other technologies at this point of time. Many other products at this point of time using technologies to ensure that no more than 20% of it has to be thrown off at the end of it. That's the only way we will be in a position to attain net zero emissions. So then comes the next issue. In light like this, what is the role of mechanical engineering? Here is my very favorite slide, which I use it very often. The left-hand side is a very traditional car of the past, and right-hand side is what the new car is. And I think we acknowledge that it's a Tesla car, a modified version of Tesla for Google for doing automatic driving. So look at the left side of the car, amount of mechanical parts that are there, it's all full of them, right? It's just not ICE, there's a gearbox, there's a powertrain, there is, for each one of the wheels, that there is a differential through which the power is being thereafter transmitted. And there is, the bigger one is the emissions. You have a tailpipe, you have a silencer, enormous number of, and then many of these are also moving parts. Wear and tear is very high. Look at the right-hand side, a clean car it's an electric vehicle. But here's the catch to it. You take off the mechanical part, still have you thrown off all the mechanical part? You've not. The car is a car. You and I have to sit in it. Potentially, I'm not talking about a futuristic dream, but these are experiments which I've seen in labs happening around the world. The car won't have a driver any longer. Why do you have a driver's seat? It'll probably, all people will sit around a circular table having a nice conversation, because you can call the car and tell it that where you need to go, and the car takes you. Again, this is not Alvin Toffler's future shock. This is reality today. And so the result is the shape of the car will change, the shape of seating will change, but mechanical engineering is required. Seat is required, right? Where would you sit otherwise? Maybe, 100 years from now, people would say you don't need to sit, you can continue to stand. There's so many things will change, but at least for the future, in the near to mid-term future, I do not think that we will throw away mechanical engineering. You look at areas in which you still continue to require mechanical engineering. The car of the future, it has to be modeled right. It has to be a piece of equipment on which it carries weight of every one of us. It's not weightless car that goes around. So therefore, the future of car has all the ingredients of the speed it has to attain. Speed attainment is all based on also computational fluid dynamics. That's the core competence of a mechanical engineer, CFD. Structural analysis. You can't do away, I'm trying to say I can model and design a car without doing the analysis in terms of the structures. Or the second one that I have is, if you look at vehicle integration and validation, cars cannot go into the streets of the world without being tested. and each one of them get tested for 100,000 hours of driving. So you and I can become probably one more generation will go by if you complete that 100 hours of testing, 100,000 hours of testing. So we simulate them. Their lab equipment which is there to do it. And so is the case with even batteries for that matter. We're saying batteries require replacement. Yes, smaller ones I can replace them. I can take a fully charged battery, push it in and take the other one out. But today it's not going to be possible with heavier ones. Would we have in the Western world, in India it's quite possible in some instances coming down all right, 10 people waiting for you to replace the battery. Therefore you require robots, and robots are the core competence of a mechanical engineer. Robotics is basically a core competence of a mechanical engineer. Or we also are seeing a fairly large amount of infrastructure that requires to be built. Infrastructure for charging the battery, and that infrastructure is on mechanical design. So therefore, for a minute, do not get overtly concerned that mechanical engineering profession is dying. It is not dying. It is, I'll come to the reason why we have fewer number of students taking mechanical engineering in a minute. It's a profession, I believe, which will be in demand for many more decades. Then you might ask this question, and especially Hemchandra Reddy also spoke about it and he knows the right numbers, he knows precisely what's happening on the ground, why mechanical engineering profession is not being seen as a profession of the future. The reason is simple. It's a demand situation. And it's also how the salaries are structured. Today, the best of salaries come in computer science. We can't stop them from happening. But you look at it from a slightly different perspective. For nation building, do you require mechanical engineers or not? The answer is yes. Cars will be there. Aeroplanes will be there. Aeroplanes require mechanical engineers. Every product which is there requires mechanical engineers. But how do we then bridge this gap? I have, of course, a very outlandish idea. And I'm trying to push this. I don't think it will happen in my generation, but I'll still do it, is that we should not have specializations in engineering. There's something called general engineering. Let the student go and learn what they like to learn. They can do anything. They can do 2 courses in mechanical engineering, 2 courses in electrical engineering. You may say, what do we call them? Who are you to call what they are? Let the person who's employing them also write down, publicize at this point of time, what the skill requirements that they have. So a combination of requirements people have versus the skill you possess is the one which matches. So I don't need to put in saying that I'm a mechanical, electrical, chemical, that specialization is not needed. And anyway, one other thing is going to happen further, is that to me, what you learn today in engineering is not going to be valid 10 years from now. Technology is changing at a pace at this point of time that you constantly need to learn. Learning for once, possessing 1 degree is not good any longer. It has to be lifelong learning. And again, technology provides that option too to you, to learn lifelong. Because people like me, I keep giving this example, I went to IIT Kanpur. I wanted to study. I went to the library. I didn't find the book. I asked this librarian, where is the book? And she said, it's just gone out. So I said, what is my plight then? She said, wait for 3 weeks. I had an intent to learn, and I didn't find the book. Tell me an instance, if you have an intent to learn, I'll show you the place you can learn, not once, twice, multiple times. And you don't need to go to the library. Trust me, I will certainly read something new as I drive back home for the next half an hour to 45 minutes, depending upon where our Honorable Chief Minister is this part of the day. I might even get stuck for an hour. He's somewhere close to my home right now, so if he's there, I might probably... But the point I'm making is, lifelong learning becomes important. So therefore, it's not, don't get overtly worried about mechanical engineering disappearing. At least in the short term, my submission to Higher Education Commission Chairman Hemchandra Reddy is that we make these courses as flexible as possible. We'll still have mechanical engineering. I'm pushing very hard right now in the IIT system. I work very closely with. I run 2 of the IITs as the chairman of the board, both IIT Roorkee as well as IIT Hyderabad. Is we are saying core competence is to be limited to just 50%. The other 50%, and Hemchandra Reddy said he's at 60%, he'll probably get down to 50%. It doesn't matter, 50 or 60. But make sure thereafter you counsel the students in such a way that they take things of interest. Actually, he said, and I joked with him, and I'd shared this with you, he said, sir, we are allowing people to even learn music. I said, to me, it's music to my ears. Because that's what I think we should allow these children to do. They should be learning what they're passionate about. Don't tell them what they need to do. You can counsel them, you can mentor them, you can guide them. But don't say, This is the structured 160 credits you should get to get an engineering degree. Only then you will pass, and that too in the engineering degree, you got to have this 4 credit courses of heat transfer. That guy said, I'm getting heated up listening to this professor. Right? My young friends are laughing it up. And it shouldn't be that. We right now do one other thing in our IIT system, it's called fractals. Heat transfer course goes in credit 1, credit 2, credit 3, credit 4. If you feel disgusted about the course at the end of 1 credit, stop it. Not only the course, you might be disgusted about the professor too. I'll go find a new guy where I go learn this 2nd credit and 3rd credit. So I think the key to us, if all these professions are to be maintained, and the Western world is doing very well, is to make sure that we allow people to have their flexibility, learn what they're passionate about. If they are music, that doesn't mean they won't run business thereafter. Music could help them to set up a music business thereafter. So therefore, I think allowing the child to have the flexibility is one. And the second one that I think is important, and let's stop there, and I've been talking for a little longer than I anticipated, is that we should allow students to work with their hands. The trend that we see all around the world is what I keep calling it as student-centric experiential learning. That's primarily say, student of the current age is different from the student we knew in the past. That's the reason why I'm saying curriculum of the past, the pedagogy of the past are not valid any longer. Student of the present, if you talk to him for more than 12 minutes, 15 minutes at a stretch and a monologue to him, I also teach, quietly the phone comes out. He's very busy, he or she is very busy with the social media thereafter. So therefore, what we like the people to do is that we need to have more amount of interactiveness. And we're saying we should move into a mode where classroom becomes homework and the homework becomes classwork. And that is where, because if I have to monologue from one direction, that can happen even in his room. It can happen in the playground. He's sitting in a corner and watching the video that you send to him, learning about knowledge. It doesn't mean that he has to be only in a classroom, sitting with friends, so that he learns. No, that is not the constraint that you should have. So therefore, I think we should, the last one I have is allow students to work with their hands. That's what we say, experimental learning. Only, it's not just the knowledge they need to get. They need to know how to build. I know I digress myself quite a bit. My last slide is what are the challenges that I have. I think I covered this. The lightweight, compactness, safety, sustainability, thermal management. But let me conclude by saying that I'm very delighted to be with all of you this morning. Thank you very much for listening to me. Certainly, I am a die-hard mechanical engineer. Having said all this, I have great pride in telling people that I am a mechanical engineer at my core. And I certainly believe that this profession won't die, but you have to constantly learn. Again, if you look at computers, they proliferate mechanical engineering. There's something called digital twins at this point of time. What is this? I create power plants in a digital mode. And who does that? If I don't have domain knowledge of mechanical engineering, I could never do that. So the profession is still there, and good luck to all of you. Thank you.